All right, so in this lecture, I want to talk about Kepler's laws and a better definition for potential energy. So Kepler's laws, there are three of them. I think the first two published 1609. So this is before Newton. I think Kepler studied under an astronomer, Tycho Brahe, and so this is before Newton and calculus. So Newton invented calculus or discovered calculus along with Leibniz, and so anyways, just to give you an idea, Kepler worked with geometry then and trigonometry, and yeah, he didn't have the fancy calculus derivatives and integrals to figure this out. Okay, so what is the first law? So Kepler's first law is pretty simple. It just states that planets move in elliptical orbits. And when they do that, about the sun, and I also want to write there, the sun is at one of the foci. So if we look at an ellipse, yes, all right, it straightened out for me. I didn't think it was going to. It's pretty dang good. I didn't draw that, but just gave that to me. What we see are two foci right here. One focus here, another focus here. And they are on the longer part. Ellipse is like a stretched out circle. And we like to call this length right here, we like to call that the major axis. And that's where our foci are. And then if we go in half this way, come on. Of course it doesn't straighten out. God, why won't it work when I want it to? All right, whatever. I'm just going to have to draw a straight line. All right, this is the minor axis. And furthermore, just in case, because I think I'm going to reference this later, this is the semi-major axis. It's just half the major axis. And this would be, right here, the semi-minor axis. Okay. Good. So, when the planet orbits the sun in an elliptical orbit, the sun itself is at one of the foci. So the sun will be right here. And the planet might be, say, here. All right. Good. Let's go ahead and move on to one thing I want to mention before we move on to second law is that the orbits are only slightly elliptical. So the reason I bring this up is because sometimes we like to approximate. And we assume the orbit is circular. A circular orbit is a special instance of an ellipse. Special case of an elliptical orbit. Now there is an equation for a circle. There's also an equation for an ellipse. I'm not going to go through that. But if you guys are interested in it, we can talk about it, or we can watch a video over it. But it's not necessary to talk about for this class, and the mathematics gets a little tricky there. So we're just gonna just as long as we understand the concept. All right. So Kepler's second law. All right. So Kepler's second law states that a line, let's see, let me write this down. A line drawn from the sun to the planet must sweep out equal areas in equal times. So what we're saying then is, if we take a look at this, let's have the sun be here, let's have our planet be here, let's have it move to right here, let's have it go this way around the ellipse. And when it does this, let's draw a line from this point to the center of the sun, to the center of the planet, and then from the center of the sun to the center, the center of this one. All right, and what we're saying then is, when the planet travels this distance, this purple arc right here, it sweeps out an area which looks like this. And this is my sun right here. I just wanted to color it. Dang, I colored over some of my yellow area though. Oh no, please. Okay, there's a button. All right. Let me just see if I can. All right, there we go. That's better. All right. So then we can say that at any 2 points, right, that this must be true. So it with any 2 times. So what I'm saying is, if the planet moves at the same speed, which is what we're assuming here, incorrectly, if we assume that incorrectly, then what we see is something like this when the planet gets here, right? We see the planet maybe here, the planet here. Right here are my 2 points. I'm saying that this purple line, this arc, is the same distance. So the planet travels the same distance in the same amount of time because it's traveling the same speed. And that means that this line from the center of the planet to the center of the sun, and from the center of the planet to the center of the sun, I'm saying that this area right here, I'll use green, is equal. Because that's what Kepler's second law states, is that a line drawn from the sun to the planet must sweep out equal areas in equal time. And if the planet was traveling the same speed, it's not, if it was, right, then this would happen, and it would not obey Kepler's second law, right? This would not work. This is yeah. So we know the planet has to change speeds as it orbits the sun, because it has to obey Kepler's second law. So what happens then, right? So, well, you can see that when the planet is further away, right, up here, that by being further away and traveling a distance, you're going to get more area, right? So what's going to have to happen is the planet is going to have to go slower when it's further away and faster when it's closer to make to follow Kepler's second law. So let's go ahead and write that down. Or we can write a consequence of Kepler's second. Is that the planet must go slower when it's further away, and faster when it's closer to the sun. All right. And let's go ahead and look at what that means then. Let's draw another ellipse. Yeah. All right. I'm going to put put some foci here. Put the sun right here. This focus. Let's go ahead and color it orange again. Missed my calling as an art teacher. All right. Okay, so here's the sun. And when the planet is, say, out here, and it travels to this distance right here, it's going to sweep out this area right here, which I'm going to go ahead and color. I think I used yellow last time. Let's go ahead and stay with that. All right. And when the planet travels the same amount of time but is closer to the sun, it has to sweep out the same exact area. So let's say it's maybe here, and it's going to go a further distance, maybe to here, and sweep out this area. Which now, this is reasonable that these areas are the same, right? If my drawing's good, I think it's decent, right? Yeah, I think that's good. I could have drawn the planet a little further along if it would have made you happy, but I think that's reasonable. Looks about the same. This looks like the yellow one's a little larger. I could fix that. You know, I just make it move a little faster. Let me see if I can get my eraser. I better have a good eraser for this, otherwise I'm going to be erasing a ton. So I'm saying, if you don't believe that that's the same area, let me go a little further then. Let me speed up this planet some. It's got to be equal areas now, right? Yeah. Look at that. Look at all that green. All right. So, yeah. So now those areas match. And you can see that the distance, the arc length that moved by the green is larger than it did over by the yellow. So this is why we get equal areas in equal times. So what we're saying is the planet moves slower here and faster here. Okay, so now let's look at Kepler's third law. And we're actually going to work off the idea that even though the planets move in elliptical orbits, we are going to assume a circular orbit for this derivation. Oh, my 3 looks like a 2. So we're going to assume circular orbit. Right, and that's okay because planetary orbits are so close to circular, and it is a special instance of elliptical orbit. All right, so we're going to assume a circular orbit, and see if you remember this from last year. Blast from the past time, right? Fg equals Fc. So what happened last year is we had an example where we would have a circular orbit, and we would then have sun at the center, and we would have a satellite or a planet orbiting out here. We knew that the two were separated by a distance that we called r. And because the object was moving in circular motion, there was a force centripetal directed into the center, which we labeled as force gravity because we never drew force centripetal on the free body diagram, right? But Fg is Fc. And because we're away from the Earth's surface, we could no longer use Fg equals mg. So this idea of gravity was good near the surface of the Earth. Right? And this comes from the idea that G is the gravitational field of the planet Earth. And what if you're not in the Earth's gravitational field? What if you're far enough away where baby G is smaller than 9.81, right? Because the further you get away from Earth, the weaker the gravitational field gets, and the weaker that number is, or the smaller that number is. So we needed a new idea for gravity, right? A better formula for universal objects, for any two objects, a universal formula that would handle planetary motion. And so this is kind of like Newton's fourth law, where we consider force gravity to equal G, the mass of one object times the mass of the other object over r squared, right? And G was this really small number called, it's called the universal gravitational constant. Whoops, I can't spell gravitation. And it's equal to 6.67 times 10 to the negative 11th. And don't worry about the units for it, it's fine. Okay, so in our special case here though, we're gonna use this new idea for G, or for Fg, but we're gonna apply it to this planet in the sun, right? So down here, let's go ahead and rewrite Fg is equal to force centripetal. Let's go ahead and plug in G, the mass of the first object, which I'll call the sun, times the mass of the second object, which is a smaller object, or little m. I'm going to go ahead and call the Earth. Or no, let's go with planet. Could be any planet. And I don't have to use a big and little m if I label them sun and planet. It's fine. Over r squared. F sub c is equal to the mass of the object in circular motion, which is the planet, times a sub c. And notice this right here, right? It's just Newton's second law, right? F sub c is equal to the mass times a sub c. All right, but we're a little better than that. We remembered, or hopefully remember from last year, that we had a mathematical expression for a sub c. And that is a sub c is equal to v squared over r. And that is the same r as what we have on the other side. So we're going to be doing some canceling here in a second. I'm actually going to hold off on the canceling to do it all at once. I want to go a little further here. Let's remember that velocity is equal to d over t. Let's remember that the distance around the circle is 2 pi times the radius. Let's remember the time to go around the circle is the period. And let's sub this 2 pi r over the period in for v. Now, obviously, we're going to have to square that mess right there. So I'm saying our formula now is going to look like this. All right, so 2 squared is 4, pi squared is pi squared, r squared is r squared, okay. The t has to get squared, period has to be squared too, and we have this r hanging out on bottom from before. So this is the v that got squared. All right, right there. Okay, so now let's get that red marker out. Let's do a little canceling, right? Okay, so mass of the planet is gone. Let's look on the right side. Do you notice the r is just on the right side? So like this squaring of the r can cancel this r on the bottom. Well, I think that's it. So go ahead and rewrite. All right, now let's go ahead and get solved for t squared. Not t, but t squared. So let's get t squared on the other side and off the bottom. Multiply both sides by t squared. Cancel, cancel. Go ahead and rewrite. Let's then multiply both sides by r squared. That will cancel these. Send it over there. We'll get r cubed. Let's then divide by g m sun. And then rewrite. Okay. Let me make this a little smaller. I knew I was gonna get rid of my whole bar there. Whoops. This is being cubed. All right, so what this is Kepler's third law. What this states is that the orbital period squared is proportional to the radius cubed. Whoops, dang. Let me rewrite it. Let me show you why it's proportional. This is in the form of y equals mx. And so your slope is also your proportionality constant. So what I'm saying here is if you graph period squared versus radius cubed, you will get a straight line that passes through the origin. And this is what we mean by proportional. Now, maybe it doesn't look like that. Maybe it's this line, or maybe it's this line. But you get the idea. It's a straight line through the origin. There's no, the y-intercept is 0. And this is why the two values are proportional. Now, if you graphed period versus r, you wouldn't get a straight line, right? You get some, I don't know what you would get. But if you graph the yellow quantity t squared versus the other yellow quantity r cubed, you will get a straight line through the origin. All right. So let's write out what Kepler's third law states then. Kepler's third law states that the orbital period I don't know why I'm writing like that. God. Squared is proportional to the radius cubed. for an ellipse, they don't have a constant radius, right? For an ellipse, r is equal to the semi-major axis. So, somewhere up here, what the heck is that drawing? So for an ellipse, that yellow line is r. Okay. The longer radius, I guess, if you want to think of the semi-major axis like that. All right, so the orbital period squared is proportional. Let me just write it one way. So we're saying one other way. T squared is proportional to r cubed. All right. Cool. Okay, I'm gonna pause it there, and then we'll come back and talk about UG and a better formula than MGH.